Welcome to Methodology for Developing Spatial Features. In this section, we will be covering what is and what differentiates one from the other in terms of the observation, the source feature, and the element occurrence. We will also discuss key terms and fields used during the development of source features. In the second section, element occurrences will be discussed. The purpose and context of this is that Biotics is based on and actually applies the standard methodology as reflected in required data fields and data analysis. And you can see some of those here. And in terms of the analysis, it applies when it considers the separation distance during the spatial analysis, which we'll get to in section 2. During today's training, we'll be discussing, we'll be introducing the methodological concepts, which are kind of hard to grasp, but you really need to know them before you go out into the field. And once you go out into the field to start collecting your own observations, those methodological concepts will be reinforced while you're collecting the required data. And then finally, those concepts will be applied when you map the data in Biotics 5 that you collected in the field. So we're going to introduce the concepts. You'll then collect data in the field, which will be using those concepts, and then you'll apply the methodology when you map source features and EOs in Biotics. So during this section, we're going over observations and source features. In terms of the mapping process, we begin with the observation, and the observation can be collected in Survey 123 or field maps or whatever alternative database that your program might be using. The observation is created to represent the raw observation data. Note that locational uncertainty is not included in the mapped feature. That information is collected as tabular data, such as precision, but it is not included in the mapped feature. And an observation can be developed for any element, whether it's a tracked species or not. In contrast, the source feature is recorded in Biotics, and it is developed from one or more observations. The locational uncertainty is always included in the mapped feature for the source feature, which ensures that the location of the underlying observation is captured within that mapped feature. Source features also can be developed for any element, including elements which are not tracked, which are partially tracked or on a watch list. And then finally, we have the element occurrence, which is also recorded within Biotics. The element occurrence is developed from one or more source features. The consistency for developing an element occurrence is achieved using standard criteria and rules of separation as defined within the EO specifications record. They are developed to define potentially viable conservation units and for tracked elements only. So EO track status is Y for yes, it's tracked, partially tracked, or on a watch list. In contrast, observations and source features can be recorded for non-tracked species. The observation feature can be a point, line, or polygon, and it represents the raw observation data. Again, locational uncertainty is not included in the mapped feature, yet that locational uncertainty can be recorded as an attribute. And typically that is recorded by the precision. And it can be developed for any element. In this example, we have a piping plover, which was recorded with the GPS with 20-meter accuracy. So the observation feature is a point, and the locational uncertainty is recorded as an attribute as 20 meters. So that mapped feature is recorded as this point here. So looking at the diagram, we have our field observation, what we actually observed in the field, and then the conceptual feature type. We'll be talking about this in greater detail. In this example, what we had was a small area because we observed a piping plover, and so it was mapped as a point observation feature. The source feature also can be a point, line, or polygon, and it reflects known occupied habitat and any area of locational uncertainty associated with the location to ensure that the actual on-the-ground location is captured. The spatial feature type depends on the locational uncertainty associated with the data and the conceptual feature type, which is based on the size of the observation compared to the minimum mapping unit of 9 meters. Now, the minimum mapping unit may vary. In Canada, I believe they use 18 meters in some provinces. The source feature can be developed for any element, and it can remain independent, or it can be used to create a new or modify an existing EO rep. Location use class, as we can see here. So this is when you're mapping in Biotics. If you map an animal, you'll have the option for location use class. Location use class applies to migratory animals that occupy disjunct locations by season. It helps to identify the season or behavior associated with that specific location, which ensures that all life cycles are considered for protection. The drop-down values reflect those defined within the EO specifications record of the element or element group. So you can see here we have a specific list that applies to the piping plover, and those are reflected within the EO specs record. The purpose of location use class is to ensure that all locations utilized throughout the entire life cycle of the animal are considered for conservation. So when we create EOs, we need to make sure that the EOs are comprised of source features of a single location use class. And the analysis will automatically group and identify source features according to that location use class or not. The minimum mapping unit is used because we can't actually represent the size of what was observed in the field on a map, right? So the field data is translated into mapped features at a reduced scale. We refer to this as the minimum mapping unit. So the minimum mapping unit is the size of the smallest feature that can be visualized or delineated with boundaries on a map of a given scale. And that minimum mapping unit differs by map scale. So typically we use 1 to 18,056 as the map scale. And if we're using that map scale, 9 meters is the smallest feature that can be seen on a map of that scale. Anything smaller would not be visible. So it is critically important and is therefore applied when we're discussing conceptual feature type, when we're using it to determine locational uncertainty type, and also when it's applied as a procedural buffer. So whenever we discuss minimum mapping unit, you should find out what your program uses. As I mentioned, within the US, I think all programs use 9 meters as their minimum mapping unit. Some Canadian provinces use a map scale of 1 to 36,000, and therefore they use a minimum mapping unit of 18 meters. So the conceptual feature type reflects the spatial feature that would result from mapping the underlying field data. It is based on the observed feature, and it's determined by comparing the size of the observed area with the minimum mapping unit for the scale of map used. So when you're out in the field, if you think of 9 meters, and if what you're observing, in this case, we had a piping plover, if that was observed as less than 9 meters, which it would be, then the conceptual feature type in that case would be a point because it is less than 9 meters. So we'll talk about that here. So in this example, what we're going to do is we're going to compare the observed area of the element. So we'll use these examples, so of the bald eagle nest, to the minimum mapping unit. And of course, the minimum mapping unit is 9 meters, and a bald eagle's nest is going to be smaller than 9 meters. And so we have a small area, and therefore our conceptual feature type is going to be a point. In the case of a linear area, that is when we have minimum mapping unit is less, a linear area is less than the minimum mapping unit, or less than 9 meters in one direction, but longer than 9 meters in another direction. So a good example of this is chicory growing along a roadbed. Chicory grows in disturbed areas, and so you'll often see it growing along a roadbed. And so that is a good example of a linear area. So that the conceptual feature type for that is a line. Our next example is a fen. So a fen is a large area in most cases, and it's greater than 9 meters in each direction. And so it is a large area, and hence the conceptual feature type is going to be a polygon. So when defining your conceptual feature type, you want to compare what you observed, the size of what you observed, to that minimum mapping unit of 9 meters. Now, locational uncertainty reflects the uncertainty of the mapped location of an observation compared with its actual on-the-ground location. It is affected primarily by survey techniques and the equipment used. So if you have a GPS waypoint with the precision of 20 meters, that is your locational uncertainty, that 20 meters. If all you know is if this is older data and it was defined as falling with quadrangle X, then your locational uncertainty is quadrangle X, or if all you know is that it was observed on Golden Pond, then your locational uncertainty is going to be Golden Pond. Now, unlike observations, source features include locational uncertainty in the mapped feature. Remember, observations reflect the raw data as the mapped feature, whereas source features always include the locational uncertainty in the mapped feature. There are 4 uncertainty types: negligible, linear, delimited, and estimated. And these are determined by the size of the observed data as compared with the minimal mapping unit, and as indicated by that conceptual feature type. And then you combine that with the amount and direction of the locational uncertainty of that given observation. And that's how we determine which locational uncertainty type we'll have. We're going to discuss each of those now. But first, where is that locational uncertainty type found? When you're creating a source feature, when you're mapping it, this is where you see those locational uncertainty type options. And this is a required field. So negligible uncertainty is when the locational variability is less than or equal to half the minimum mapping unit, or less than or equal to 4.5 meters in any direction. The uncertainty is applied to the entire feature, and depending on the size of what you originally observed, that could result in a point, line, or polygon source feature. So, for example, if we have a bald eagle nest that was recorded with a sub-meter GPS unit, then we could have negligible uncertainty as our locational uncertainty type. In this case, we have our conceptual feature type of point. There were 12 plants reproducing in good quality habitat within a well-protected and extensive park. The plants are growing on a floodplain at UTM, and then we have the coordinates. So we can see this point right here is our negligible source feature. For linear uncertainty, this is when the locational variability is greater than half the minimum mapping unit, only along a single axis. So in this case, the endpoints can be based on either physical features or the biologist's determination, such as if you're starting at a bridge and then going down 20 meters, for example. The resulting source feature in this instance is going to be linear, and the locational uncertainty type is going to be linear. The resulting source feature is going to be line. So an example of this would be oysters along a riverbed. And so what is mapped as the source feature would be that section of the riverbed in which the oysters were observed. An example of that is with the mocha emerald dragonfly. The conceptual feature type was point, because these are just little dragonflies, but they were observed in the brooks associated with the lakes. And so they were observed somewhere along these brooks. And so what we're going to map is the brooks, because all we know is that they were observed somewhere within these brooks associated with the lakes. So we have linear locational uncertainty. For delimited, this is when the locational variability is greater than half the minimum mapping unit in more than one direction, and the location can be delimited by a boundary. So you can easily look at that and delimit the boundary. This could be based on physical features or the biologist's determination. And the resulting source feature in this instance is going to be a polygon. So, for example, if we see a bog turtle observed somewhere within Lake Ojibwa, and we don't have any more information than that, then what we would do is we would map Lake Ojibwa, because we are reflecting that locational uncertainty of where it is within Lake Ojibwa within that source feature. So in this example, we have a shallow emergent marsh. The conceptual feature type is a polygon because the marsh is greater than 9 meters. And we have a single patch of grass and sedge-dominated open wetland within the floodplain of Michigan Hollow Creek. So what they mapped was that floodplain, and they were able to delimit that floodplain. Now, if they had had a GPS unit, or if they were mapping it with Survey 123 or field maps and actually walked around that location, then they would also have a delimited locational uncertainty, but it would be more accurate. In this case, all we know is that it was somewhere within this floodplain, and so they mapped the floodplain. And finally, estimated locational uncertainty type is when the locational variability is greater than half the minimum mapping unit. So greater than 4.5 meters in more than one direction, and a boundary cannot be drawn to delimit or define the boundaries. So in that case, the uncertainty distance is specified by either by the biologist or the tool that is being used, whether it be a GPS or a pad or your cell phone, which will record the precision. The distance in this case is going to automatically be applied to the entire feature as a buffer. And the application will do that. So what you do is you map either the original point, line, or polygon, and then Biotics will automatically buffer that pre-source feature by the given locational accuracy distance, locational uncertainty distance, and buffer the feature for you. So in this case, we have a Kentucky warbler, the conceptual feature type. This is a bird, so it was a point. And it said the birds were reported near Ossining, Westchester County. The locational uncertainty distance was 2,400 meters. And so there's a point probably dropped at Ossining, which we can see up there. And then it was buffered to 2,400 meters because they didn't have really any better information than that. And you'll see this often with historical data. So if you recognize this from within your own Biotics database, these big buffered points typically reflect historical data. Representation accuracy indicates the level of accuracy associated with the source feature. I'm just going to go back for a second. When we look at that feature, we have no idea how accurate that is. looking at it, we can kind of assume that it's inaccurate, but we really don't know, which is why we have representation accuracy to reflect the accuracy of the source feature. So representation accuracy varies on the basis of the area that was observed to be occupied by the element, reflected by that conceptual feature type, and how large that area is relative to the area contained within the footprint of the source feature. So that final mapped source feature, what is the footprint of that compared to the size of what you observed in the field? We compared the difference of the two sizes to reflect the locational uncertainty, and we use the representation accuracy to provide a common index for consistent comparison. And that enables correct analysis and interpretation. So there are values of very high, high, medium, low, and very low. So we have these 4 different examples. We can assume this is very high. We can assume that's very low. For this one, we really don't know, nor do we know for this one. So that's why we have representation accuracy to help us define that. We have a representation accuracy dichotomous key that helps you define that accuracy value. So now if we go back to the source feature, so we've been talking about the source feature. So now if we look at all of these concepts that we just discussed and compare it to what we originally observed, which was that piping plover nest, where we recorded a GPS accuracy of 20 meters. We have the location use class that we would have to define. Was this a breeding spot, non-breeding, migratory stopover, or undetermined? We would have to select one of those. That is required. We also need to define the conceptual feature type. So if you recall, our conceptual feature type reflects the size of what we observed. Now, in this case, we observed that piping plover, and so that's a small area that was observed. And our locational uncertainty type is defined by the GPS unit, and we're applying that 20-meter accuracy to the entire point feature. And so that is estimated uncertainty. Now remember, had it been less than or equal to 4.5 meters, it could have been considered negligible, but this is well beyond that. And since the locational uncertainty is being applied to the entire feature, we have estimated uncertainty with a locational uncertainty distance of 20 meters. So we're going to map the pre-source feature as that point, that location where we observed it, and the Biotics will automatically apply that 20-meter locational uncertainty distance to develop the polygonal source feature. So our pre-source feature type is going to be a point. It is then buffered by 20 meters by the system, and the resulting source feature is a polygon. And according to that representation accuracy dichotomous key that we just saw before, the representation accuracy for this turns out to be high. And so now if we look at that entire diagram, we can see that we started with a small area. This was our piping plover. which was obviously less than 9 meters in each dimension. It was a small area. Because it was a small area, our conceptual feature type is point. The locational uncertainty type we had was 20 meters, and we couldn't delimit it. And so it automatically is estimated because that 20 meters is then going to be applied to that entire feature. Our pre-source feature in this case is a point, and the locational uncertainty distance of 20 meters is applied to it by the system. And so the resulting source feature is a polygon. So that is the end of section 1. Thank you for attending, and you can follow up with section 2 to learn more about element occurrences. Thank you.